Hi students, all of you welcome. Welcome to Sunil Engineering Academy. I am Sunil Kumar Bandaru. Students, in the chemistry, recently we have started atomic theory. In that, some topics are pending. Now we are going to discuss those. Okay. And if you want previous session, just click on the playlist. You can find out all the previous sessions. Okay. Let us start the session, guys. So let me check up to which we have completed. Law of constant proportions, Dalton atomic theory, fundamental particles, J.J. Thomson model, Rutherford model, Bohr's atomic model. Okay. Now we are going to discuss electrons distribution. Electrons distribution. Okay, so in the electron distribution, the very important question is the maximum number of electrons present in a shell. The maximum number of electrons present in a shell. Okay, that is 2n square. Note down that point. The maximum number of electrons present in a shell or orbit. In a shell or orbit is nothing but 2n square. 2n square. So n is nothing but orbit number. N is nothing but orbit or shell number. Shell number. Okay, if you can consider it is the first orbit. First orbit, or you can consider first shell. Then n is equal to 1. So then maximum number of electrons present, that is 2n square na, that is 2 into 1 square, that is equal to 2. So in case of n is equal to 1, that is 2n square, that is equal to 2. So then what is that shell? N is equal to 1 means you can say k shell. K shell. We have the numbers n is equal to 1 means K shell, n is equal to 2 means L shell, n is equal to 3 means M shell, n is equal to 4 means En shell. Sorry, KLMN. Okay, correct only. Okay, so then n is equal to 2 in the sense that is L shell. What is the number of electrons, maximum number of electrons present? 2 into 2 square, that is equal to 4 into 2, 8. So in the L shell, maximum number of electrons present are 8. If n is equal to 3, that is M shell. It is very important. One of the previous bit. Okay, 2 into 3 square, that is 9 into 2, 18. So in the M shell, maximum number of electrons present are 18. Okay, in the same way n is equal to 4, that is N shell. N shell, it is 2 into 4 square. 4 square means 16 into 2, 32. So maximum number of electrons present are 32. Okay. So this formula is very important. Note down this formula. Okay, don't forget. If n is equal to 1, it is a K shell. N is equal to L shell. N is equal to 3, M shell. N is equal to 4, N shell. Okay. And sometimes we are also getting the question that the number of electrons present in outermost orbit, that is nothing but valency electrons. Okay. Valency electrons. So note down one important point here. This is the first point, and coming to second point, the maximum number of electrons that can be accommodated in the outermost orbit. What is the maximum number of electrons present in the outermost orbit? That is maximum 8 only. So we can consider that one as octet. That one as octet. Outermost orbit. If they are asking only the outermost orbit, that is 8. Electrons are, third point, note down. Electrons are first accommodated in inner shell and then outer shell that means the shells are filled as stepwise. Shells are filled in a stepwise. Okay, and what you can say the valency electrons? Valency is nothing but the electrons present in outermost orbit. The electrons present in outermost orbit are nothing but valency electrons. For example, if we have inner side K shell, L shell, M shell are there. So this is the outermost shell or outermost orbit. The electrons present in this orbit are nothing but can say valency electrons. Nothing but can say valency electrons. Okay. After this, now we are going to discuss some important terminology, guys. Some important terminology, that is atomic number, atomic mass, isobar, isotone, okay, isotopes, and all those. Okay, and before that, it is better to discuss some rules for filling of electrons. Some rules for filling of electrons. Already we are discussing about the electronic distribution, electrons distribution. So now we are going to discuss some rules for filling electrons. Rules for filling electrons. So what are the rules for filling electrons? We have first important rule, Aufbau principle. Second one, Hund's rule. Third one, Pauli's exclusion principle. Okay, so these three rules we have. The first one very important, that is Aufbau principle. Aufbau principle. It gives the idea how the electrons are going to fill in the different orbitals. Okay. So according to this, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and P starts from here, 2p. Wait, I need some gap. 2p, 3p, 4p, 5p, 6p, 7p, and 3d, 4d, 5d, 6d, 4f, and 5f. How the electrons are going to be filled? First of all, those are going to be enter into 1s. Okay, those are going to be filled into 1s. After 1s, they will be enter into 2s. Okay, after 2s, they will be enter into 2p. After 2p, that will be 3c, 3s, and then 3p, 4s. Okay, 3p, 4s. After 4s, it will be enter into 3d, and then 4p, and then 5s. Okay, after 5s, it enter into 4d, and then 5p, and then 6s. Okay, after 6s, it will be enter into 4f, 5d, 6p, and 7s in the cross manner. Okay, and after that 5f, 6d, 7p, and 8s. Okay, so that means first of all, they will be orbitals are filled in the first lower energies. Okay, so lower energies are filled first, after that higher energies are going to be filled. So note on that point. That means here, first of all, 1s is lower energy, and then 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s, in the order. Last we have 8s. Okay, so like that they will be filled. So note on the point here, orbitals. What are the orbitals we have? S orbital, P orbital, D orbital, F orbital. Okay, orbitals are filled in the order of increasing, the order of their increasing energy levels, their increasing energies. That is nothing but, first of all, low energy orbitals are going to be filled. So that is orbitals of lower energy are filled first. Okay, and when it is filled up completely, that is lower orbitals are filled up completely, then remaining enter into the orbital of next energy, the orbital of next higher energy. Okay, for example, if you can consider a sodium 11, 23. So atomic number is 11 now. So it has 11 electrons in the sense. First of all, it will fill it completely with S lower energy, and then 2s2, and then 2p6. Correct? First 1s, 2s, and then 2p. After that 3s. Okay, 2p6, and then 3s1. Correct? Yes, 3, 2 after 2p, 3s. 3s1. 3s1. Okay, so here the electron which is present in outermost orbit, it is the outermost orbit. Outermost orbit, it has one electron, so it is considered as valency electron. Considered as valency electron. Okay, so we can fill maximum electrons in s orbital. S orbital maximum range is 2 only. If you can consider p orbital, that maximum electrons you can fill 6. D orbital maximum we can fill 10. F orbital maximum we can fill 14. Okay, can fill 14. And sometimes they will also ask a question that shape of orbitals. Shape of orbital. If you can consider s orbital, it is spherical shape, round, spherical in shape. P orbital, dumbbell in shape, dumbbell shape. D orbital, double dumbbell shape. Okay, and finally F orbital, it has a shape, but we cannot define. It has the shape, but we cannot define. So indefinite shape. Indefinite shape. Okay, so these are very, very important here. Now the second rule. This is the first rule. The second rule. Second rule is Hunt's rule. This is half occupied condition. Hund's rule of occupied condition. Okay, or you can say it is a singly occupied condition or of occupied condition. Singly occupied condition. That means if you have S, P, D orbitals are there, in each orbital at least one electron should be filled. At least one electron should be filled. That means let us take an example, then you will get an idea. If you can consider a nitrogen, atomic number 7, mass number is 14. So it has total 7. So then what is the configuration? 1s2, 2s2, 2p3, correct? 2p3. So then what will be the electronic configuration? Electronic configuration, if you can consider 1s, 2s and 2p. 2p has 3 na? 1, 2, 3. So then according to this 1s is 2 means it is completely filled. 2s means here also 2 electrons. Here 2p3. 3 means 3 electrons. 1, 2, 3. Okay, so the electronic configuration may be like this. But according to Hund's rule, Hund's say that singly occupied condition. Here remaining one is empty now, but it is always trying to occupy at least one electron in this. So this one electron is moving from this place to this place and it will become singly occupied condition and becomes more stable. So according to Hund's rule, one electron is moving from 2p to 2p1 to 2p3. So like that. 1s, 2s, 2p has 3 again. So 1s is completely, 2s is completely the 2p, one electron here, one electron here. One electron is moving from this place to this place now. So here. So this is the correct one as per the Hund's rule. Okay. This is the Hund's rule. At least try to occupy a single electron. Okay. So note down here. Pairing of electrons in the orbitals belongs to same subshells. Subshells are nothing but you can say SPDF. Okay, pairing of electrons in the orbital belongs to same subshell, does not takes place until each orbital belongs to each orbital belongs to that subshell has got one electron each. That means if we have 2p, in this 2p it is divided into 3. Here it must be at least one electron is filled here. After that one electron is filled here. After that one electron is filled here. After that only, at least if it has one electron, after that one only, if any other electron is there, that is filled like this. Okay, that is filled like this. Okay, so it is not correct. So as per the Hund's rule, if we have any two are filled, that one will be moved to another one. That means now we can say at least one electron is filled. At least one electron is filled. That is the point here. Okay, the point here. Now after this, the another rule or principle is there, that is nothing but Pauli's extension principle. Pauli's extension or exclusion. You can say any manner. Okay, it is a very simple thing. If you can consider in any electronic distribution, we have the quantum numbers now. Principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. If you can consider any configuration, all the four not be same. Okay, all the four quantum numbers not be same. That is the point here. Okay, note down the point here. This one as given after quantum numbers are discovered. After quantum numbers. Don't worry, we will also discuss the quantum numbers here. It was given after the introduction of concept of quantum numbers. Introduction of concept of quantum numbers. Okay, the number of electrons to be filled, in various orbitals, are restricted by the exclusion principle, that is given by Pauli's, given by the scientist Pauli, given in 1926. Okay, according to Pauli's no two electron no two electron in an atom can have same set of all the four quantum numbers. Okay, all the four quantum numbers. If two electrons have same three quantum numbers, the other one should be different. Okay, if two electrons have same values of principal quantum number, azimuthal quantum number, magnetic quantum number, that means three quantum numbers. Then they must differ in the value of spin quantum number. Okay, that is fourth number. Okay, so if you can consider in any atom, that is if those have same values of principal, azimuthal, magnetic quantum numbers, the fourth quantum number must be different. That is given in the Pauli's extension principle or exclusion principle. Okay. So while discussing the MCQs, then you will get idea about what is the question you are getting. Okay, what is the question you are getting? Now coming to the quantum numbers. Okay, so it is better to discuss these quantum numbers in the next session. Quantum numbers and atomic number, atomic mass, and all those. Okay, I'm going to end the session now. We will discuss remaining in the next session. All of you, thank you so much for watching. Take care. Bye, guys.